I have spent 28 years at the Oak Ridge National Lab, during which time I met many of the former MSRE leaders, and unfortunately, many of them are not with us anymore. In particular, one of the people that I met early on when I got to ORNL was Dick Ingle and Mac Toth. Mac is still around. Dick died a year and a half ago, and the two of them are the ones that really gave me my education in the molten salt systems and circulation of molten salts. All right, today I represent ThorCon, looking at a thorium converter reactor. Our present target is for that market to be markets where people want electricity at a low cost. In fact, we're going to be competing against coal as the target competitor and want to produce electricity at a cost that is cheaper than coal. Towards that end, the molten salt reactor is ideal because you can pump things around. You don't need a mausoleum to maintain the system. You can build it somewhere else and tow it, in our case, ship it. And in our case, we are looking at building it with the block technology that has been developed for the shipbuilding industry, which is very rapid, so we can support the fact that it's a molten salt reactor and built on block technology allows us the opportunity to have a very low cost and fortunately compete with coal. Okay, so what is our intention here? Our intention is to produce, at least for demonstration purposes, a prototype that will be built in a hull, in a shipyard, under the block technology approach. We'll pre-test that. We'll then tow that to Indonesia, and notice the market we have chosen is one that wants power, but does not want power based upon coal because they have the example of China facing them. We will settle that offshore and power it up. So essentially, we plan to tow 174 by 76 meters ship, if you want to call it that way. That is essentially a 500 megawatt power plant to site and power it up and demonstrate that. Once we have demonstrated that, we can then move on. So that's our present target. Within that power unit, which represents about 557 megawatts of thermal energy, the way ThorCon's concept is that we will have the plant operated in such a way that each power module is composed of what we are calling 2 cans. We will be operating 1 can for 4 years, move the fuel over to the second can, and allow the first can to cool down in place before taking it out to take it back to the factory. So the modular concept is important to us, and you'll see why on my next slide, because that allows us to do things like ensure that we're going to get that reactor can out of the system before failure has occurred, assuming that we have done our modeling right. So how do we convert the heat generated within the reactor? We have 3 salt loops. The molten salt loop, which contains the fissile material within it, exchanges its heat with a non-radioactive salt in the second loop, which then converts that to, takes this heat across to a solar salt loop, the sodium potassium nitrate salt. Before that converts this heat over with a water loop. The reason for that sodium potassium nitrate salt, it gives us some isolation between the nuclear side and the non-nuclear side of the system. And secondly, any tritium that may have transported itself across all those nice little tricks that we're going to impose to collect tritium should be oxidized in the nitrate, sodium nitrate salt, and therefore will be finally stopped, the small amount that gets there. Our overall thermal efficiency of the system as modeled is approximately 47.7%, assuming we have a 20-degree input water, and a little bit lower, about 46.4%, assuming we have about a 30-degree centigrade input water. Most likely we will be closer to 30 degrees in Indonesia. So the modularity, as I spoke of earlier, is implemented via the can. The can, essentially shown here in red, is the structure. And within that can, we have what we call Because we did not want to use the term pressure vessel, we call it a pot. Within that pot is the reactor. It's not a pressure vessel. We operate under about 3 bar, 4 bar at the most. It's not a pressure vessel, it's a can. Within that is the moderator. In our case, it's graphite, just like in the molten salt reactor experiment, up along which the molten salt flows. Below the pot are the same freeze valves as, or similar to what was used in the MSRE, except we have gone to 4 on each one. And we can therefore drain, even if 3 fails, we can still drain. We have redundancy inside there. And that drains into our dump tank. We have now segmented the dump tank in the bottom there. And all of this sits within a cold wall. The cold wall is fundamental to our removal of heat from the system. The cold wall takes the heat away from the outside of the can. It takes the heat away from the dump tanks. The cold wall operates passively. This is an absolutely passive device. You can shut everything else down. It will keep on circulating the water up the cold wall and into the coolant pond, which is shown off on the right there. That coolant pond has a capacity, if we have nothing else going on and we cannot refill it, for 147 days of coolant. That is way past what happened at Fukushima. Okay? We can cool. And I haven't yet taken into account, and I shall avoid it for the time being, the water we have in the basement, which gives us additional time. So we can walk away from this plant for a long time, allow things to cool down if something happens, which is unlikely to occur, and still be okay without releasing anything to the atmosphere. And again, all of this is by natural circulation, no pumps to provide the cooling. What is the target right now? Our target for the next step is to build a non-fissile test plant using the same technology and by the block technology to build it. And once we build this, we will test this non-fissile test plant in all possible manner that we can think of, and some that we presently cannot conceive of, to ensure that physically and from a control point of view, in the absence of fission, we can control this pot, this arrangement, this non-fissile plant. Once we have completed that, we can then move on to a next step, which would be building a plant in which we would put fissile material into it and move on. Here is the update where we are at, and the first 2 bullets on this slide, I will go into a little bit more detail, but I'm going to keep us on time. We have done some modeling, and we have had some modeling done for us on a Fukushima type accident, and that has shown that we are okay with our reactor as designed. We've also had some simulation done for towing this hull through the North Atlantic storms. And that may say, wait a minute, you guys said you're going to Indonesia, why North Atlantic? North Atlantic, if you can travel your ship through the North Atlantic storm, you are seaworthy for the world. If you can't survive North Atlantic storms, you are now restricted in where you can ship your ship. So therefore, that's what it was modeled on. We also have modeled an aircraft strike onto that hull and see what would happen, and I'll show you some results for that. We also have ongoing 2 GAIN projects with the Argonne National Laboratory. One of them concerns salt property measurements. We are not using the molten salt that was used in the molten salt reactor, which was FLIBE. We have a slightly different system. Right now, it's a sodium beryllium fluoride salt. And therefore, we need some properties taken from that. Now, mind you, work was done on that back in the MSRE days. There are numbers out there for it, but there are some properties we need that are missing. So we are trying to get those measured. The second project at the Argonne National Lab is some development of electrochemical sensors in order to measure chemistry, measure redox potential. The redox potential is critical for us controlling things like corrosion and other reactions within the system, and solubility of fission products in solution, et cetera, et cetera. And one of the things we are also extremely interested in is, can we detect the evolving plutonium level in our salt? Remember now, we're going to be trying to detect a very small quantity, a very, very, very small quantity of plutonium in a vast sea of uranium. So this is an interesting question as to how that can be done. But if it can be done, it gives us another way of keeping track of what's in that fuel and what's going on with it, so we know how to handle it. The final thing that has occurred recently that I want to talk about, I shan't present any actual data on that, is a study performed by the Indonesian agency TEAC10 for the government in Indonesia. They looked at whether ThorCon's claims about its safety, its cost, its supply chain, etc., was truly valid. Are we selling a case? Are we overselling our position, overselling our case, etc.? That report, or that 8-month study, came back and said, oh, ThorCon is not really overselling. Those guys know what they're doing, and they're presently writing up that report. It is our understanding that they will make a recommendation to the President of Indonesia to move forward with ThorCon as the nuclear plant for Indonesia, the first nuclear power plant. I should back up. Indonesia does have isotope medical production reactors. Stepping back to the first one on that slide, the ThorCon Fukushima Response, what the analysis shows is that, let's assume we have the first case. Earthquake occurs, and the earthquake sensors on our system triggers a salt, the freeze valves to open up, and we begin to dump the salt. It also releases the shutdown rods, 3 of them. They're redundant. We only need 1, but we have 3 for redundancy. They release the rods. They open up the freeze valves. We begin to dump the salt. We therefore know we have lost all power, and we have lost all cooling in the primary loop as a result of that. Essentially, what is the end result? The end result is that the reactor is in a safe configuration. The salt is in the dump tank. It is radiating heat quietly, without concern, passively, to that cold wall, and it's going up into the cold wall and going this way. Okay. The reactor is safe. Our calculation says that we are approximately 750 degrees max in the fuel is the maximum temperature for not a very long time either, but that's the max temperature we have achieved. Our system can withstand that without a problem. In fact, we could probably go back up and restart that reactor. We will restart that one. A scenario above that is you have a total system blackout. So you've lost power. You've lost your auxiliary boilers. You have no power. Okay? In this particular case, we make the assumption that because of that, what we have is that the shutdown rods still release. They come on down. Of course, the temperature is rising, even though the shutdown rods are down. So the freeze valve will open up. We dump the salt. The reactor is once more in a safe configuration. Radiated heat now lovely to the cold wall, and we are good. Maximum temperature in the fuel as a result of that is approximately 850 degrees C. With the materials we are using, we're not particularly concerned. The third scenario is the worst one, in which you've also lost you have a total stational blackout, but now your rods don't release. The SID case, it just stuck. All 3 rods stuck. Remember, we only need 1, but all 3 of them are stuck. In that case, our maximum fuel temperature rises to 1,000 degrees C. Again, the freeze valves will open up and dump the salt, but we have gotten to 1,000 degrees C. We end up with about 0.5% creep on our materials. For all the mechanical engineers and material engineers in site, no big deal. 0.5% creep. It's almost like, okay, that occurred. However, we will replace that can because the control rods failed to release. So we will condemn that can, take it out, and move on, reinstall a new can inside there. Notice that in the particular one I'm showing, which is the very first scenario, we are looking at about 7 minutes at which we begin that release from the system. Moving on to the second analysis that was done for us, the towing of the hull through the North Atlantic storm. Analysis shows that this vessel, this hull, whatever you want to call it, can withstand 1 G forces for days. Now, let me repeat that. 1 G forces for days. Okay? And it's fine. A typical reactor, about 0.4 Gs for seconds. At most, a minute is the requirement on that. So we can really rough this thing up and get it to where we gotta go, it will function. The third scenario that was looked at is the aircraft strike. So this is your scenario of 9/11. The aircraft comes flying into your building. An aircraft, for all intents and purposes, is a skin on a frame. So the main damage comes from the engines. Of course, in 9/11, the fuel also caused a problem with the heat generation there. But we are flying a 8-ton engine into our vessel. Okay. The 8-ton engine strikes our vessel. And in this case, our sandwich structure with sand filling, it would be the same if we had concrete inside it, but with sand, there are reasons for using sand because you can then pump things out if you need to refloat and stuff like that. But with the sand inside there, the maximum penetration when that engine hits the structure at 200 meters per second is 200 millimeters. That's your maximum penetration into our structure. Our maximum deflection on the inner wall of the sandwich is 300 millimeters. Again, not much. The net result is that we have no effect as a result of that strike on our silo. Okay, so you said that's great. Okay, but remember, the silo surrounds the cold wall, that important mechanism we have for keeping the reactor cool. So that's fine. And that cold wall surrounds the can. So again, the can is fine. We may want to do some inspections, but the can is fine. And within that is a primary loop containing the fission products and the fissile material. That also will be fine as a result of the aircraft strike. Okay. So the net result of all of these analyses is so far our projections are correct. And we will keep on going. We keep on moving. We are going down that long and winding road, as all of us know who is in this business. But we keep putting one foot in front of the other, and we're moving forward. Thank you.
Did the Indonesian nuclear regulator have a look at your design and provide any feedback?
Minimal look at the design. That is the sort of the follow-on step to the present review that Babatin and Bapen had looked at. So they did not look at the detailed aspects of the design from a point of view of the reactor physics performance and so forth, but they looked at it from a point of view of the safety. Does it meet the safety requirements?
Dane, how many of these reactors can you generate with your current model? Let's say per year or per decade or whatever.
A small, efficient shipyard can generate somewhere between 10 to 20 plants of 1 gigawatt size per year.
When will you have your first commercial plant operational, or at least one for concept purposes?
Okay. What Indonesia would like is that they can say that they will have a commercial plant producing the electricity for them by 2026, which means that we have to have a demonstration plant that we can test in all possible failure modes somewhere in the time frame of 2024 to 2025.
Can you discuss price points?
We have met, our projections are better than the price requirement for electricity by the Indonesian government. They have a target. We have shown that we can be below that, but I don't want to give you an exact number.
Is your plan to load the fissile salt at the shipyard, or
No.
put it in when you get to the destination?
Yes, there is something not shown in my quick overview there, is that we have a separate approach, what we operating what we call a can ship, that will actually bring the cans into that site with its fissile material either in it or separate from it, depending upon whether we are doing an upgrade, sorry, not an upgrade, having to add makeup fuel or not to that can as it is operating. So we do have to do some makeup fuel as it is operating. But right now the plan is to bring that separate from the fuel, bring the fuel separate.
If you guys have access to shipyards, I would love to see you guys explain this and say, here's a real shipyard in operation, because I don't think most of us here have any real sense of what a shipyard is like and all the machines and stuff.
I did have pictures of that and I stripped them out. One of the reasons I stripped it out is that I had a picture from the Hyundai shipyard in it, and I hadn't gotten permission to use the picture. So I stripped that one out completely.
One more question.
Just because of the size you described, how do you get it to land? And can you get it inland?
The one I showed you is for balancing out into the water. So we're actually going to be, that plant is going to sit in the sea, in the ocean, the sea, whatever you want to call it, and bring the power in. For the land version of that, the blocks will be put together in as large as we can carry once we get to the site with the necessary hauling equipment, and then the final structure welded together there. It will, yes, it is, the construction is modular, yes. The block construction is for those of you all unfamiliar with it, a block construction of a ship is a modular type construction where you put things together, much like the way Clayton Homes operates in East Tennessee.
You said that you're gonna shift the salt every 4 years to a new can. Are you then gonna keep the same graphite for all those 4 years? Or
No.
planning?
The graphite life we are projecting right now is 4 years.
Okay.
The whole of that can is pulled out, including its fuel and everything else, and taken back.
If the graphite life is 4 years,
Yes.
is it that the system is going to be running for more than 4 years or not?
When I think of system, I think about the whole plant, including the power generation part and everything else. The actual can, that red part that I showed you on those pictures, which is what we are calling the can, that will be removed every 4 years. Well, actually every 8 years, because we're going to do 4 years cool down once we drain the salt out of it and let it sit there for 4 years to cool down so that the radioactivity in it decreases significantly, makes it easier for handling. But that whole piece gets removed.
So there's a shutdown for that for a period?
Of the can, not of the power plant. Okay, so can A has operated for 4 years, produced power. I take my salt out of that can and I just let it sit. That salt goes into can B. Can B starts producing electricity. And 4 years later, I take can A out. I put another can into that position for can A.
Very good. I can't thank you enough, Dane.